Good afternoon and good morning, everyone. Appreciate your attending to our webinar. I'm Li Xin, the lead analyst of Singapore Membrane Consortium. Before our webinar, I would like to introduce the housekeeping rules. The webinar will be recorded, but the recording, presentations, and Q&A transcript will be shared with the registered attendees. Secondly, the audience will be mute. If you have any questions about the talk, please use the raise hand function during the Q&A session. I will post the questions, or you can type your questions in the chat box below. And these questions will be answered live at the end of the talk. I also encourage you to do the post-webinar survey. The download link for the recording, presentations, and Q&A transcript will be available after the completion of the survey. So next, let's welcome Joanne, the Program Director of Singapore Membrane Consortium, to introduce the overall topic of this webinar.
Good afternoon, everyone, and to our attendees from Europe, very good morning. If you're calling from anywhere else, a very good day or good evening. My name is Joanne. I run the program office at the Singapore Membrane Consortium, or SGMEM. So briefly, SGMEM is a national consortium funded by the National Research Foundation since September 2018. And we have two key mandates. One, we work to bring membrane research and innovations from our universities towards product commercialization. Secondly, we aim to expand the use case of membranes beyond the traditional water sector. Now, in this backdrop, there is a growing urgency to reduce the impact of human activities that has gone unchecked for far too long, which we are starting to experience the brunt of it in the form of erratic weather and natural disasters, which in turn affects the supply of human essentials like food crops and water. Singapore is not immune to this. This is why for our first webinar of this year, we wanted to delve into technologies that, although may not be able to eliminate entirely the ways we are going about producing our goods and services, but it can slow down or significantly reduce the use of fossil feedstocks, energy consumption, and precious minerals, as well as reduce the amount of effluents and emissions that are being generated. With this, I'm very pleased to have Prof. Yang Xing, Prof. Chua Tian, and Mr. Kieran Oh today with us, each sharing their work and processes that in some way is helping us to find better and more sustainable solutions to activities that support our basic survival. I'll hand this back to Sin for the speaker's introduction.
Okay, thank you, Joanne, for the warm introduction about SGM and the topic of this webinar. So it's my pleasure to introduce our first presenter of the day, who is Professor Yang Xing. Dr. Yang joined as the Associate Professor in the Development of Chemical Engineering in Belgium of KU Leuven since 2020. She is the trained chemical engineer through her bachelor study in Zhejiang University in China, master in Chinese Academy of Science, and a PhD in Nanyang Technological University in Singapore. Prior to joining KU Leuven, she worked at Victoria University in Australia for 6 years and was a senior research fellow and lecturer. Also thereafter hold a joint research position between Deakin University and Victoria University. Dr. Yang has more than 10 years of this international discipline research experience focusing on the development of functional membranes and hybrid separation systems for metal, mineral, research recovery, bioseparation, and water purification by combining the power of experimental and modeling. She is currently the editor board member of Desalination Journal and the early career editor board member of Journal of Membrane Science. So, Professor Yang Xing, it's yours.
Thank you very much, Sing, for your kind introduction. I would like to, share my screen first. Hi, floating. So, will you be able to see that screen?
Yeah, I can.
Okay, yeah. Thank you very much, Sing, for your kind introduction, and thank you, Joanne and the team for your kind invitation for this to speak at this webinar. And yeah, and good morning, good afternoon, and good evening for all the participants who are interested in this theme or topic. So I would like to start with a little more on the fundamental side of research. That's, of course, we are more on the academic side. So we would like to share how we use the process intensification, which is more a classic concept of chemical engineering, to actually design a membrane-based systems, and how we'll focus on the solute harvesting, not just by recovering the materials, but also harvest the solids itself. And our team is also part of the efforts of the Institute for Sustainable Metals and Minerals, that is also has a large effort in resource recovery. So that's I would like to mention. So before I actually start the research introduction, I would like to start with a very general introduction, because we are in the north in Europe now, and you are in the south, more in the middle of the globe. So that I would like to sort of introduce ourselves. So this is we are from the KU Leuven. It's also called the University of Leuven. It's if you can see this picture here, is one of the iconic building in one of the iconic buildings in Leuven. It's founded in 1425. It's the same time as when the university was founded. So it's nearly 600 years old. And then we have a very nice location, which is in a nice city of Leuven. This is one of the oldest city halls in the world. For some reason, I actually have two pictures of the same building at different timing of the year. So it's a very, very nice location, which is in the center of Leuven. And this is one of the oldest churches in Europe as well. And we have very distinct seasons, which is very different from Singapore, where I was also studying. So the most beautiful season is autumn. That's also my favorite season, that is always golden and really, really warm. We also have the best beer in the world. And also the best chocolate in the world. So if you ever come by Europe, and you will be most welcome to visit us in Belgium, and really nice to show you around, and also not just our research, but enjoy Leuven itself. So our research group, we are a very young group, as Singh mentioned, that I actually joined in 2020. I moved from Australia, so we started, but we're growing at a very fast speed. So in the past year and a half, so we're building the critical mass. So, and if you can see the background behind us is actually showing the process evolution of the process intensification. That is quite the image in front of our building. So yeah, so and then next I will talk about how we actually utilize, or we see the concept of process intensification in designing a membrane system to make it more efficient, and not just from energy point of view, but also from the throughput, from production point of view, and some future perspectives. So what is actually process intensification? So as a chemical engineer by training, then I can see the paradigm has been shifted in the last 2 decades. In a broader sense, so PI is actually referring to making changes to manufacturing or processing design for substantially improving its energy efficiency, cost effectiveness, or enhancements of other qualities. So there are 3 levels of definition. So if you look at the bottom, look at the scales of process intensification, they actually go to the very small scale, which is the molecular or micro scale, where you look at the molecular interactions, and then further you look at membranes and look at reactions, particles, and further you can actually go onto the system level, where you have a larger scale process intensification. So our membrane research is actually sitting quite perfectly along the full scale of the process intensification scheme. And from the approach point of view, that we also look at the structure, the energy, and synergy between different parameters, and the time as well. So basically, it also describes very well in terms of how we actually could do in membrane-based research. So what do we do in KU Leuven, our group? So we work for HER. HER means health, environment, and resource. So basically, we focus on fractionating biomolecules to actually, such as antibodies, that actually can be used as a therapeutic solution. So that is linked to the health solution. And we also look at water purification that actually they can help resolve the water crisis issue, recover the valuable materials from there, that we are very strong on circular economy. That is also part of the efforts under the SIM Square, as I mentioned. So we recover from the battery materials. That is, eventually what our efforts is working towards making our Earth a better living space. So our research is covered under the two umbrellas, that is two strategic directions in Europe. So bioscience and environment, matter, materials, and energy. So we basically use this multi-scale process intensification for system integration and optimization. And we base on the two methodologies or two toolbox that we use. One is the numerical modeling. Second is looking at the functionality and the design, using the functionality of composite materials to actually design a membrane, and also design the separation devices to make it more efficiently run. So we focus on three clusters, and the first cluster is recovering valuable metals and minerals from natural and waste sources, which I will go a bit deeper. And we also look at fractionation of biomolecules from biopharmaceutical streams. And we focus also on high strength wastewater. That again is linked with resource recovery. So we not just focus on purifying the water, but also recovering the values from there. So we basically deal with liquid separation. So not just water, but also energy related elements, chemicals, and pharmaceuticals, anything that we could actually, any solids we could actually harvest from the solid streams. So we work with quite concentrated streams as well. So as I said, our objectives is actually use the process intensification to see how we can actually design a more energy efficient hybrid membrane systems. As a chemical engineer, we also would not forget about other classical chemical processes. We will hybridize the membrane concept with the concepts of crystallization, chromatography, absorption, extraction to achieve the separation and eventually achieve purified products. So how do we do that? Basically, so if you look at from the micro to macro level, so in the micro level, what we do is we use transport modeling to understand what is happening when the solids is transporting through the membrane, and what is actually the membrane chemistry, the surface chemistry is doing in the separation, and also how the micro level hydrodynamics is actually affecting the micro level transport. So, and understand what are the limiting factors in the separation. We also looked at that functionalization of the membrane to overcome low effectiveness, and the kinetics and dynamics that's actually affecting a long-term separation, a long-term performance of the membrane. So combining the understanding on those two levels, then we can design really efficient membranes, and combining the membrane functionality and also the flow dynamics. On a higher level, that we also look at systematic analysis using also process simulation to actually design a system that can actually overcome low energy efficiency and eventually achieve the design of a larger scale system. So as I mentioned, we have three clusters in the group at the moment. So the first cluster is looking into the fractionation of biomolecules. We're looking to purifying, not just purifying their bioactive components such as antibiotics and proteins and viral vectors, and also harvest them as crystal products. And our strategy is also around 3 pillars, what we call. So we look into how we can design the structure, because for bioseparation is very different from ion separation. So we need very porous structure. We look into the synergy of the structure and the surface chemistry, where we can design very accurate capture and release of the proteins or the biomolecules. And we also build transport model to actually look into, okay, what is actually, what are the most influential parameters, and how we can actually design the structure of the membrane and the surface functionality, and also the module to actually achieve the most efficient separation. So these are all very influential factors that we identify. So what are our research strategies? In bioseparation, we focus on nanofibrous membranes. We electrospin that membranes, and we functionalize them to actually have very high density of active functional groups. And then we also evaluate them in terms of the binding of the membrane towards the bioactive compounds. So our aim is actually to develop this new generation membrane that can actually have a 3-dimensional structure that can actually have very high binding capacity, which is the current limit. So as I said, we use electrospinning. That's our facility. And because the reason we use that, because it can actually be very versatile in terms of tailoring the membrane, not just the hydrophilicity or hydrophobicity, because we need very hydrophilic surface in this case. We also need very high surface area, because it promotes the interaction of the solids with the biomolecules. So, and this also gives us very high ligand density. That means the density of the functional groups. So we focus on very highly porous membranes, and they have very narrow pore size distribution. So all the molecules will have equal interaction with their functional groups on the surface. So by combining our understanding of polymer solution properties and our understanding on fabrication parameters, we can actually develop or design a series of morphology structure that can have different benefits under different treating at different solutes or different molecules. So a very versatile technology. In the end, then we will be able to link the performance of the membrane, which is mainly concerning the binding of their biomolecules, with the structure parameter, with the surface chemistry. And we also use the transport modeling to actually to see how we can optimize these parameters in the end. So the second cluster we have is about ion resource recovery, that we focus quite a bit on recovering the values from the electronics and battery waste. So that's and also, of course, the toxic heavy metal removal from the wastewater. It's a dual purpose research basically. So we focus on designing ion selective membranes, right? So not just the for example, not just the ion exchange membrane, but is targeting at a certain ion that we are of interest or of value. And we also create closed loop processes that we can actually fractionate those ions in a very high purity and eventually crystallize them as their products, as their solute. So because in general, the throughput of such membranes is always of concern, that we look into also ways to actually intensify the transport. We also design a facilitated transport membrane process that can actually combine the conventional extraction concepts with the electro-driven processes to actually further enhance the mass transfer and reduce the resistance. So we not just focus on dilute streams, as I mentioned, so we also looking into the solute harvesting, zero liquid discharge. So I So in order to do so, that we need to understand the crystallization kinetics, right? We need to understand how the synergy of the solute transport or the solvent transport through the membrane, that is also has a synergy with the crystallization and also with the hydrodynamics in the system, right? So that is very fundamental understanding that can actually help us to design a better membrane module to actually avoid or delay the occurrence of supersaturation or the termination of a membrane performance, and we can eventually design a continuous membrane crystallization systems using also other types of intensification strategies in this case. So we evaluate the system performance to see, okay, what actually are the most energy consuming elements and how we can design the configurations or tailor the configurations to actually achieve better energy efficiency. So that is based on the sensitivity analysis and to actually achieve a sustainable harvesting of the crystals. Eventually we'll be able to deliver crystal products and also in the meantime also could recover acids and volatiles. So for the crystal products we have minerals and we also worked in active pharmaceutical ingredients. That is also because the shape of the crystals, what we call polymorph, is also very important. So that is, we evaluate that harvest in terms of the crystal quality, right? The size distribution and the yield and the shape. So these are all very important indicators. So the third project cluster, we focus on high throughput desalination and membranes and the systems. So we, my background actually, when I was in NTU, I actually focus on membrane distillation for seawater desalination and also harvesting of minerals from the seawater or brine sources. So, so basically, my strategy is there's a lot of, I did also modeling that is to understand the mass and heat transfer during this processes. Based on our understanding on mass and heat transfer, we know which parameters that can be tangibly adjusted, right? So we, based on the understanding, we design high throughput microporous or membrane distillation membranes to actually not focus on tips or nips, which are the traditional fabrication methods. We focus on the combined methods, which is called N-tips. It's non-solvent thermal induced phase separation that can actually create a very asymmetric structure. Then with a relatively dense layer, a surface layer, while you have a very highly connected pore structure in the bulk, and that actually greatly reduce the mass transfer resistance. Other than that, we also look into how we can sustain this high throughput, right? So we look into strategies that can actually reduce the adhesion of valence onto the surface, and they're using the responsive chemistry. And we also look into the reactive chemistry or surface chemistry that can actually actively reduce the attachment of valence. So that in overall, that is to enhance the separation and sustain the separation in a high throughput state. So now I would like to briefly go through the 3 generations of high throughput MD membranes that we developed under the N-tips method. And the first generation was the basic one. So it's a single layer asymmetric hydrophobic membrane where we can actually create, as I said, a very asymmetric structure that can actually have very high liquid to entry pressure because the wetting issue is a big one in membrane distillation, and we'll be able to create a very high permeability in as compared to literature at that time. And the second generation is we're looking to, okay, the trade-off between the heat and mass transferring membrane distillation is really bothering everyone. So we design a dual structure where we have a hydrophobic layer that can actually resist the wetting and suffice the principle of membrane distillation. And we also have a hydrophilic layer that can actually trade off or offset that loss of the conductive heat. So, and then based on this principle, we designed this dual structure that actually could actually minimize the mass transfer resistance and can achieve very high permeability that is even more than a single layer, much higher than a single layer. So the third generation is we focus on improving the mechanical strength while keeping the high permeability. So what we do is we design a pseudogenous structure that can actually have a very thin hydrophobic layer and also a pseudogenous support layer that is embedding the fabric. So in the end, that you'll be able to also reduce the mass transfer resistance while increasing the mechanical strength to more than 10 times than the conventional type of membranes. So overall, I think that's very much I would like to share about 3 research classes that we have. And that the idea behind is we use the multi-scale process intensification strategy to actually guide. Basically, everything is coming from how we understand about the transport mechanism and to translate them into the tangible separation indicators and or design parameters that can actually help us design better systems. So all in all, our perspectives is that the transport modeling can be a very important tool to understand the performance limiting factors in mass and heat transfer in membrane that is particularly concerning many membrane processes that could be translated into tangible membrane properties, as I mentioned. So micro to milli-level PI strategies can be applied to actually manipulate the membrane structure and chemistry design to actually design the interaction of the solids and to manipulate the interactions between solids and the membrane surfaces. However, that understanding or the synergy between the micro level and the macro level fluid dynamics and how it's actually influencing the throughput and also the interaction of the solids, this is yet to be identified. This is some area that could be further studied. On the system level, where the PI strategy can also assist in terms of how we design the system parameters, how we design the modules, or how we design the system as an integration. So as an integrated units, and to actually improve the energy efficiency and produce more controllable process routes. So for example, we can actually control the crystal forming in a certain way, in a polymorph in a certain way without interrupting the quality of the crystals. So lastly, I would like to acknowledge our funding agency and also, throughout my journey, the students and colleagues in NTU and also in Australia. And we have joint programs with 2 universities in China, and of course, my students in KU Leuven. So that's our picture in front of the Ehrenberg Castle. And also we have a bunch of master's students who also work with us. So that's very much I would like to share. Thank you very much for bearing with me, and I would like to take any questions at the end.
Okay, thank you very much, Professor Yang Xin. It's a really nice talk. It covers many systematic research on 3 technical clusters, such as the bioseparation, resource recovery, and desalination. So we have one question for you from the audience. Mm-hmm. So the one is, does process intensification impact the scale up of the technology, such as the surface modification?
Do you mean the changes, the surface modification strategy, would that influence the energy efficiency of the system?
Yeah, true. It means the surface modification, is it possible to impact the scale up of your technology?
Yeah, I think so, because I mean, of course, it's because if you functionalize a membrane in a different way, then the throughput of the membrane will be different, right? Because when we design a system that we'll like to consider, a few key performance indicators or outputs of the system, which is the energy efficiency and the production efficiency, or that is mainly related to the quality of the products, right? So I think that having a surface modify membrane that may have a higher efficiency would definitely change the picture.
Yeah, that's true. I agree with you. The surface modification sometimes is quite difficult to scale up, because we have to ensure the uniform of the surface. I mean the surface modification. So okay, thank you for your answers. So So thank you very much. It's my honor. Yeah, it's my honor to introduce our second speaker, Professor Zhuo Jian. Dr. Zhuo Jian received his PhD in chemical engineering from National University of Singapore for his work on membrane technologies. His areas of expertise are membrane process, membrane formation, hollow fiber spinning, membrane transport mechanisms, and water treatment. He has invented several membranes for evaporations and membrane desalination applications. He also has extensive chemical engineering knowledge and experience process design, unit operation, process technology, and system optimization. Currently, Dr. Zhuo is an assistant professor in Singapore Institute of Technology, working closely with industry on membrane technology for liquid-liquid separation, wastewater treatment, desalination, and resource recovery, as well as membrane process for sustainable food development. Okay, Professor Zhuo Jian, the floor is yours.
Thank you, Dr. Lee. Let me share the slides first. Okay, can you see the slides? Okay, thanks. Yeah, thanks for the nice introduction, and also inviting me for this opportunity to give the talk in this webinar. So today, the topic that I'm going to focus on is membrane desalination for water treatments and resource recovery. So firstly, we are going a little bit introduction on the university as well as on the backgrounds for why we are using this technology. Then later on, we are going to talk a little bit on the case study, which is a pilot scale study for the membrane desalination for real seawater desalination application. So firstly, something about the Singapore Institute of Technology. So different from the KU Leuven, so Singapore Institute of Technology is quite a new university. So KU Leuven have a very long history. SIT has only about history of around 10 years. Then it became the 5th autonomous university of Singapore in the year of 2014. So it's actually less than 10 years from then until now. Then for this new university, there are a lot of things happening over here. And the positioning of the new university is we are focused on the applied learning. So SIT vision itself to be the leader in the innovation, leading by the integration for learning, industry, and community. So we focus on applied learning as well as focus on the applied research, which means we are going to work very closely with industry to solve the present and also the current issues that the industry partners may facing. So we do have a lot of collaboration with different industrial partners. So if we have any issues of the things that we want to solve at the moment, actually SIT will provide a lot of universe opportunities to help us to do the collaboration to solve the issues at a fast pace. Then regarding to the areas that we are having, so for the cluster that I'm in is the food, chemical, and biotechnology cluster, and we are having more specialization under this one cluster. We have pharmaceutical engineering, we have food technology, then we also have chemical engineering. So in addition to the traditional chemical engineering, we focus something on the pharmaceutical and the food technology. This will also provide us the opportunity to work with the respective industries. For example, for the pharmaceutical engineering, we are working very closely with the local pharmaceutical companies to solve the issues of the production issue or the modular production, process intensification, or even the improvements on the solvent recovery, on the water and wastewater treatments, and also the production of the biomolecules such as the proteins, antibody, antigens. And so these are the collaboration with pharmaceutical engineering programs. Then in addition to that, we are also working on the food technology. And so I'm having the collaboration with the industry on this one for the alternative protein production. So we produce the protein from the plant-based protein source so that we can have a wide variety of the source of the proteins. So this is also promoted by Singapore government. We need to reach 30 by 30, 30% by the year 2030 for the local supply of foods. We are working very closely with the industry in this area. Then, of course, on the traditional chemical engineering part, we also have a lot of activities going on using the sustainability, wastewater treatments, zero liquid discharge, this kind of areas. So currently, SIT has satellite campus around the Singapore, but we are moving to the new campus in Pango in about 2 years' time. So the new campus will be designed together with the Pango Digital District, so that there will be a living lab over there where we'll have a lot of more resources, labs, and opportunities to work with the communities over there and the industries as well. So with that, I'd like to move on to talk a little bit on the topics of today. So we talk about the water and resource recovery. Either water and resource are quite closely linked together. So for the water, let's take a look at the water issue currently. So water is become water security and also scarcity issue has become one of the major problems. Around 1 million of people are suffering from the deficiency of fresh water. Then this issue will be actually intensified because of the developments of the industrial developments and also the increase in the population. So this is the water issue. And how do we deal with the water issue? We need to have a different source of waters. So for example, in Singapore, we are having 4 national taps that will provide the water for the water demands, which includes importation from the nearby country. We can have also a natural reservoir. We also have the new water system that will reclaim the water from the domestic wastewater. Then we also have the desalination plants where we recover water from the seawater. However, with the increased activities in the economy, then the water demands were going to increase sharply. And to ensure that we are having the water security, we do need to diversify our water supply. So in addition to this, probably we should think about, do we still have other sources for water? For example, the industrial wastewater. Currently, the industrial wastewater in Singapore, the recovery rate is rather low. So most of the industrial wastewater is not going to be recovered, and it's going to sometimes be sent to incineration, sometimes to be treated and to be released. Then the other one is the reverse osmosis plant. So for the reverse osmosis plant, it actually has been treated from previous all the steps of pretreatments. So we have already spent the effort to do the pretreatments. Then now, can we still recover something valuable, some more water from the plant? So these are some potential resources of the water. In addition to the water, so these resources can also provide opportunity for the resource recovery. For the industrial wastewater, many of the industrial wastewater actually contains metals, like the petrochemical industry, pharmaceutical industry. So they use a lot of metals, for example, in the catalyst, platinum, palladium are the most commonly used catalysts for the chemical reactions, as well as for the synthesis of the pharmaceutical compounds. Then if this catalyst after that catalyst is being used, they will end up into the wastewater stream. Then how do they deal with the wastewater? If it directly threw away, it a waste of the precious metal. And on the other hand, it will also have some contamination to the environment. So currently, actually, we are having this collaboration with the pharmaceutical industry, trying to recover the precious metals from their wastewater. So of course, membrane technology is one of the way. Then we need to use membrane technology to combine with other methods to come up with a package for the solution to do the recovery. So this is doing the recovery as well as the environmental issue. Similarly, for the reverse osmosis. So the reverse osmosis brine contains a high concentration of NaCl. Then the management of the brine is currently an issue. So one of this way to use the RO brine is to produce caustic soda. However, the majority of the RO brine is still released back to the marine environment. This will cause the imbalance in the marine environment, so that the ecosystem in the marine system probably will have some disruptions. So in order to solve this issue and to get the resource and the water out of the wastewater streams, actually we are focusing on this three: water recovery, resource recovery, and also to reduce the environment impacts from these wastewater streams. Then how can we do it? There are many technologies, as we mentioned just now. So here, we just want to focus on one of them, which is using the membrane technology, because the membrane distillation technology has quite a few advantages compared to the other technologies. So it will be having the mild operation condition, which means it doesn't have any pressure requirements. Then the temperature is in the range of 50 degrees to about 80 degrees, so mild temperature, and 100% rejection to the source, so that after the treatment, then the water from the pyramid will not contain any heavy metals, any precious metals, can be released, disposed directly, or can be reused and recycled. Then it's also not limited by the source concentration. So we can do the concentration of the source to a very high concentration, or even near to the saturation points. So the osmotic pressure for the source concentration, source solution will not be the limiting factor. And the ability to couple with the low-grade heats because of the mild operation condition. And of course, this technology will also have its own so-called disadvantage. So one of the major disadvantage is the energy requirements. So currently for MD process, it is still an energy-intensive process. So to solve this issue, we have different directions to work on towards solving this issue. So one is to work on the process design, process integration, so that we can have a better process control to recover the process waste heat. Then on the other hand, because of the mild operation condition, we also can tap on the waste heat or waste energy. So one example is over here, the cold energy from the LNG, liquid natural gas gasification process. So this energy can be used to cool down the water in the pyramid, so that we can receive the water vapor from the feed solution. Then for the hot energy, we can also tap on the solar energy. So in this case, the solar energy is used to directly heat up the feed solution. And the efficiency for doing it is much better than we use the solar energy to convert it into the electricity. So we are going to have a better and higher efficiency if we use it for direct heating. So these are the ways that actually can help to reduce the energy consumption of this process. So next, we are trying to just focus on one case study that is using the membrane distillation combined with the crystallizer for the treatment of the seawater brine to produce clean water as well as salts that of economical values from the pilot scale process. So this shows the general process design concepts. In the center, we are having the membrane destination and the crystallizer. Then the brine will directly be used. So in this case, we are using the real seawater brine collected from the local desalination plants. Then from after the process, the product will be just clean water and the sea salts, which will have the tendency to push it to zero liquid discharge. And the membrane is one of the key parts for the membrane destination process. For this particular project, the membrane that we are using is the commercial Stormex hollow fiber membranes, which is provided by Membership Innovations. So Membership Innovation is working in the MD and zero liquid discharge area. And it is a startup company in Singapore. And we are working very closely with the industry and as well as so that we are also working very closely with the MEMSIF. So SID have for the collaboration. Then for the seawater, as we mentioned, is directly collected from the local plants, which has the total dissolved solids about 45K ppm. And firstly, we have done quite a lot of analysis and characterization for the membrane that we obtain from MEMSIF. So for example, the morphology study, pore size, porosity, tensile kind of property study. So here I just want to show one of the studies that is on the morphological stability study. So the morphological stability study is we use the membrane to be immersed into different pH solution to test the long-term stability. So this study is important because the different pH solution in the future, in the actual process, we probably need to use acid condition or alkaline condition to do the cleaning of the membranes, so that in the actual process, the membrane need to withstand a certain degree of this solution and with a better stability. Then from the stability test, after about 10 weeks of the testing, actually we can see that the length and the mass of the membranes that we are using, there is almost no change. So it is very consistent from the beginning to the end. If we examine very closely to the initial period of the length change, probably we can see a slight decrease trend over here. This decrease trend is also very small. It's about 1 to 2%, and is likely due to the initial conditioning and the initial pore shrinkage during the initial periods. However, after that, the entire process become quite stable, and we didn't see any large variations. So which means the membrane is stable under these pH conditions from pH 1 to pH 10. As well as for the tensile strength test, we also tested it under different solutions to see whether that solution will have any adverse effects on the membrane tensile property. And after the test for another 10 weeks, actually we see that the tensile strength remains about 3 megapascal. So this is on the one hand very stable, on the other hand is a very strong membranes that can be used in the membrane destination process. Then regarding to the overall pilot scale process, here is the process design or process flow diagram. On the left-hand side, we are having our MD process. So the MD, we have the membrane over here. Then the membrane area is 0.2 meters square with the heating to 65 degrees C. Then we also have for the permit for the MD process, which is a partial vacuum. This is a quite a low vacuum, 80 kPa, which is about negative 0.2 bar. So this low vacuum is normally used in the industry to save the energy. So we don't want to use it like we are doing the vacuum in the laboratory. Usually we pull it down to a very high vacuum, but that one is not going to be very efficient in the industrial process. Then for the cooling water, room temperature cooling water is circulated over here to do the collection of the permit site. So after we have pulled it down from the membrane, so we use room temperature water to do the collection. Then on the right-hand side, there is a crystallizer. So the crystallizer will help to reduce the temperature after we have concentrated the solution. Then the crystal will form and will be separated by gravity. So this is by a special design in the crystallizer. Then the leftover one will be pumped back to the process to do the continuous concentration process. So this entire process can be operated continuously. On the one hand, the water can be recovered. Then on the other hand, the crystal can be continuously produced. And here shows you the actual pilot scale equipments. So on the left-hand side, we have for the membrane. And on the right-hand side, we are having the crystallizer. For the process-wise, we have tested it for the 280 hours operation, and the data is collected hourly. And during the process, due to the safety reason, the process is the operation is in the daytime, so about 8 hours a day. Then it was stopped during the nighttime, and we also have designed a simple rinsing protocol, simple washing protocol for the membranes. So at the end of the day, the membrane is immersed into just tap water for a few minutes. Then the membrane is plugged back into the system. And for the entire duration of the process, about 280 hours, the average flux that obtained is around 3.7 liter per meter square per hour. And we do not see any net change or net fluctuation on the flux, which shows the stability of the membranes. So it's not a sharp decrease or sharp increase. And from the product TDS, we also can observe the stability. The TDS is always below 5, which means the product is meeting the WHO requirements of smaller than 500 ppm. So the produced water is actually fresh water. We also like to compare the energy efficiency by calculating the actual flux or versus the theoretical flux. So the theoretical flux is calculated based on the 100% energy recovery, energy efficiency. However, as we can see, the theoretical flux is always smaller than the actual flux. This is due to we cannot achieve the 100% energy efficiency. So this one can help us to see how the energy efficiency varied along the operation. On average, we get 62% energy efficiency, which is reasonable for a process without any energy recovery system. And one note for here is actually when the actual flux decreases, the energy efficiency also decreases. So this is very important in the process design, because if the membrane is not stable, the flux variation, the energy efficiency is also sacrificed. And to increase the energy efficiency, we can have different methods. And we can have a method to prevent the heat loss. We can have integration for the heat recovery system design. Here is one method to do the integration for the heat recovery design to recover the energy from the permeate site. So if we consider the recovery during the calculation, we can increase the GOR, gain output ratio of the entire process to around 2. So for the entire process, which is just one step of the energy integration. So lastly, the process, after the entire process for the concentration, the free water is concentrated to around 2,200 ppt, which is close to the saturation points already. And we have collected the kgs of the source. So the source is a wet source. But this entire process demonstrates that the membrane destination integrated crystallizer can have the capability to continuously produce the water and source at the same time, to push to the near zero liquid discharge status. So due to the time limits, I think I will not go to details for that. So just have a short conclusion and prospects. So from this pilot scales design, we have demonstrated the capability of using the MD to have water and resource recovery. However, there will still be some improvements we have to make, such as the process design to have energy recovery, to see more energy efficient process. Then the potential for this process is not only limited to the RO brand, so it can be extended to the recovery of other precious metals from other type of wastewater solutions. So we are also working on this extension parts to recover resources from the pharmaceutical wastewater or other industrial wastewater. Yeah. So I think with that, I'd like to conclude my presentation, and thanks everyone for your attention.
Thank you very much. Thank you for the very nice presentation from Professor Zhuo Jian. And yeah, it's really covered a lot of knowledge about the membrane distillation and some case studies for treating the RO brands. So thank you very much. So actually, really, we have some questions from our audience, but yeah, consider the time, we have to put it in the Q&A sessions. Okay, so it's my pleasure to introduce our third presenter, who is Mr. Karen. He obtained the bachelor's degree in chemical and biomolecule engineering from National University of Singapore. Currently, he is the process engineer and the strategic development engineer at Santa. His interests are to develop the new membrane applications in niche industries, oversee development, and manage upcoming projects in niche and upcoming fields, and drive the development of novel composite membrane materials. Okay, Mr. Karen, please.
Thank you so much, Dr. Lee Sing. And thanks so much to Dr. Yang Xing and as well as Dr. Zhuo Jian for the interesting presentation just now. So, and thanks SGMM for inviting us over for a presentation on this. So let me just start off with a short introduction about what Santa does, so that then we can move into a short introduction of myself before we move in to talk about global trends as well as zero liquid discharge and how membrane can work on with zero liquid discharge, and then provide a good overview of the return on investments with the membrane application before we jump onto a conclusion. So for a short introduction about Santa, I guess all I would say is that we are a leading global leader and in development of advanced membrane materials. We started in 1996. So when we started in 1996, we actually ventured a lot into niche process designs. So if you think about it, a lot of the process design when we talk about membranes, it's always on water, resource recovery. But on another perspective, we can see it as a very niche separation technique that can focus on items such as vitamin C, proteins, and a lot of other more I would say industrialized product or consumer-based products. So if we're going to dive back in onto water treatment, so our water treatment, we have been doing water treatment with membranes ever since 2003, where we moved most of our operations back to China, and then we have been exploring because the market is really much larger there. So, and then we have a lot of global footprints as well throughout the years of operations. So just a bit of introduction about myself. I was a graduate from NUS in chemical engineering. I did a lot of works with process designs, with membranes, and in the water treatment field, doing a lot of PUB tenders, working on a lot of niche applications as well. And then I got exposed to this very specialized water treatment technique that we call zero liquid discharge. So I will talk a lot more about zero liquid discharge in this presentation. So let's just move on towards the global trends of water treatment. So something very fundamental is the water types. So if we're going to look at this, there's only that 3% of water that we can really use, right? Because the other 97% is salt water from the sea. And then if you go look at the spread of water scarcity around the world, we suddenly realize that although water is very available in Singapore, to us, when just on the tap, can have a very stable source of water. But in fact, water scarcity is really spread out throughout the world. So if we're going to dive a lot deeper into that, we can see that if we look at annual discharge, industrial, domestic, we are looking at something near 359 billion cubic meters a year. And then of these 359 cubic meters, 359 billion cubic meters a year, only 52% of the discharge is being treated. So there's still a huge gap of water treatment around the world. So if we look into the discharge and how it's being treated, a lot of things will start to show up. So biologics, the use of bacteria to break down COD and BOD, your membranes to mechanically, physically stop the contaminants from passing through the membranes, and then chemical reactions where we use some chemical properties like the solubility constants to remove the contaminants. So if we're going to look worldwide and global, we start to see some of the law implementation and how it affects what the global trends of water treatment are. So in 1972, the US actually released the Clean Water Act of 1972. So this is actually the start point of people starting looking into more wastewater treatment, how are we going to reuse the water. And then in 1996, integrated wastewater discharge standards from China, GB 8978-1996 was introduced. Then China started to hop on and then start to regulate their wastewater discharge, so protecting the environment. So in 2011, so let's just fast forward and just ignore the in-betweens. Let's just fast forward 2011. Because water is getting more and more stable, people are looking, and industrial growth is getting more and more stable as well. People are spending a lot more time and a lot more, putting a lot more emphasis on how this wastewater discharge and how the industrialization has been affecting the environment. So then in that case, the manufacturing giants in China and India, they have been putting a lot more emphasis on zero liquid discharge. And then in 2011, the China Ministry of Ecology and Environment and State Administration actually pushed out seven different mandatory national standards to protect the water discharge. This also includes the amount of water to be discharged, as well as tightening all the parameters to be, of the discharged water. So when we look into sustainability and why the government are doing this, we actually will see that this is actually just reduce the amount of waste to protect the environment, to create cleaner source of water for everyone, of course. And then if you're going to look at into the byproducts, there's also always the production of secondary products there. So what are really the water treatments that's going on around the world? First, seawater T Cell. So this is the act of just taking seawater, concentrating the salt in one stream and then removing the salt in another, so that this water can be used for drinking. So if you think about this, if we are discharging toxic waste from industries back into the sea, and then we are just taking the seawater for desalination, then this creates a lot of trouble for everyone, all the way down to the consumer end. So if you look at it, look at another arm of it, the municipal wastewater treatment or the industrial wastewater treatment for discharge. So similarly here, if we are discharging water, toxic waste into the environment, then this is only going to loop it back to us. So what we are doing is basically putting in more biological treatment here, trying to break down the COD, BOD, remove some of the toxic waste before it's pumped back into the environment. So if we're going to look slightly deeper, some industrial wastewater will be treated for reuse. So meaning they produce the wastewater, they want to stop using industrial water, which means taking water from the utilities. They can actually treat the water back for their own reuse. So in this case, the zero liquid discharge is actually a spin-off of process reuse, because all the water being produced in ZLD, in zero liquid discharge, will be put back to reuse. And then what we are so-called discharging is only solid waste. So just now I've mentioned about what basically zero liquid discharge is basically making use of all water, putting it back to discharge, producing any solid waste. So this is a very specially curated process design so that we can minimize the harm that we are putting back to the environment. So right now, because like I said previously, the manufacturing, the industrialization is getting more and more stable. People are putting more and more emphasis on environmental impacts, as well as more focus on sustainability. That's why ZLD is becoming a more and more popular process that a lot of industries is looking for. So right now, if we're going to look into zero liquid discharge and how zero liquid discharge is being marketed in the industry, right? We always talk about taking the wastewater, running some minimum pre-treatment in there so that it doesn't harm the MVR, and then put it through a very energy intensive steps of MVR, thermal evaporator, centrifuge, so that they can get out the solid waste while recycling most of the condensate for reuse. So, but this whole component is basically you just taking a heating source and you trying to evaporate away all the water while keeping the solids. So then this becomes a very, very energy intensive. It can even range up to 70 kilowatt hour per meter cube of water treated. So this is a very hefty cost for anyone to start putting this into their own process lines. If I'm going to so-called do zero liquid discharge, taking up 70 kilowatt hours of energy per meter cube of water, buying water is much cheaper than that. And really, does zero liquid discharge give me any market value in there? These are what business owners will start to think about. And the answer to this is most of the time, it doesn't give a good return on investments. So how do membrane actually come in and help this? So how do actually membranes come in and help this whole process? Is we start to analyze what is actually the factors affecting the energy consumption for the evaporation components. Is it capacity? Is it the composition? So where should we really focus on to help cut costs on this? So to help cut costs on these energy intensive components, is actually we need to dive way deeper into the pre-treatment portions. So then we are going to look into something called brine concentration. So how do we really do brine concentration to extend that MVR will become much cheaper? So normally when we look at brine concentration, there's a few parameters we are looking at: TDS, COD, hardness, presence of any more toxic metals. So then how do we really stop this? So first, definitely reverse osmosis. Then second, nanofiltration, if we are going to look into production of secondary products. So if I want to just isolate out sodium chloride from the other salts, nanofiltration will be a good choice. Then chemical sedimentation. If I am looking at some water sources that is very high in concentration of calcium, magnesium, then yes, I need to do some chemical sedimentation, and then we might be able to implement not just a sedimentation tank here, but some more niche type membranes, like the ceramic membranes that sometimes holding for hardness removal. And then if you're looking at high COD, high BODs, then we need to include things like MBR. So let me just explain a bit more about how reverse osmosis will help brine concentration. So the basic concept of reverse osmosis is basically you're just applying pressure through a membrane. Because the pore size are small, the salt particles, the TDS, tend to get retained back in the reject site, and then water gets flushed through. So what happens here is if we are going to try to push it to the brink, we can try to get very high recoveries just for the brine concentration. We can get very, very little flow rates for the concentrate side, for the retentate side. And then when we run the retentate through the MVR, the capacity will be much smaller. So what RO actually potentially serve is we'll try to reduce the water entering the MVR by about 80%, sometimes 90%, depending on what the inlet TDS is, so that we can minimize the cost of the MVR. So sometimes we'll start to look at external loops and internal loops for different stages of different passes of RO, so that we can overall increase the water recovery here. So like I said just now, if you're going to look into nanofiltration in brine concentration, when I already concentrate my brine, there's always the salts, sodium, there's always sodium ions, magnesium ions, sulfate ions, calcium ions. So if I'm going to use nanofiltration here, then definitely I'm going to stop the magnesium, I'm going to stop the calcium, I'm going to stop the sulfates. Probably only sodium chloride will pass through, or any other smaller molecule, smaller ions. So in this case, I started to look into things like salt separation, byproduct recovery. So in any case, if sodium chloride or sodium sulfates are very expensive in the area, such actions might lead you to an additional source of income. So when we apply membranes in the whole brine concentration zone, we start to see that, okay, there are less and less concentrate passing through the MVR. And then if after we pass through the MVR, there's a very huge component that can be reused, producing solids. If the solids can be reused, there's extra cost we achieve there. And then if we are going to compare the energy consumption for the brine versus the MVR, we're going to see that it's very probable that the brine concentration can actually reduce more than 50% or even up to 50% of the MVR cost. It's either cheaper or it's lower in operation costs. So there's a lot of more benefits for us to run membranes compared with just a pure MVR reaction. So then I mentioned about all these cost savings, right? So how good does it actually look on the return on investments? So this is just one of the rough ROIs that I did for one of my projects. So when we came out with this ROI, we are looking at an evaporator cost of about 3.5 million for this capacity. If you're going to use membranes, definitely my cost, I'm just not reducing the initial investments on evaporators. So definitely I'll be dumping in more money for just the membrane systems, but we do see a huge cut in operation costs. So when we start to analyze the ROI and the break-even period, we can see that it actually lies just slightly after 4 years. It haven't even reached the 5th year, haven't even reached the 5th month, and we actually can get back what we actually spent on the membranes. And then if you're going to look into the whole systems, including evaporator, how it look. Systems I've designed, an ROI probably range between 3 to 5 years, sometimes even way lesser. Then this creates a lot of economical impact for any industrialized partners. So come back to a conclusion, why people are starting to look into zero liquid discharge more is because more and more people are putting emphasis on sustainability. Water cost it's a very huge cost for many industries as well as the government putting extra pressure on discharge requirements. People are looking into how to reuse water, how to maximize the water reuse, looking at zero liquid discharge. And then when they start looking at zero liquid discharge, they realize that, oh, shit, there's a lot of cost just by us implementing evaporators. So this is where industry partners like the membrane suppliers or the membrane designers comes in and then help to say that, okay, this, when we look in pre-treatment, when we look in brine concentration, we can actually mitigate a lot of the issues that is currently up there for zero liquid discharge. And then this becomes a very well-rounded process design for anyone that tries to implement zero liquid discharge. So I guess I can hand back the time to SG Mem. Just a short note, if you guys are coming to SLWW, you guys can visit us at the booth B2K44, and then we'll be more than willing to share more about the designs or more about products, including the ceramics or some of the niche products that we are pushing out recently, our graphene membranes. Probably they're still much more in the pilot stage, but you guys can come down and take a look at how it looks like and how it runs. Yep, I guess that's all from me.
Okay, thank you very much, Mr. Karen. And it's really nice presentation to cover a lot of the introduction about the DLD systems. So for now, here is the Q&A sessions, and I welcome any questions from the audience about the three speakers in cover their background, research, and the showcase. So maybe you can type the questions in the Q&A the box, and you also can raise your hand function. So okay, let's check the questions. Actually, I have one question for Mr. Karen. And you mentioned that a lot of technology, memory technology can be used in the ZLD systems. For example, you can use the RO membrane, NF membrane, but you know that this membrane really has the concentration limitation. So what's your comment or your opinion to how to select the different membrane, based on the different fit concentration to select which one is better to fit the VLD system?
So for the question, how do we actually select the membranes?
Yeah, correct. Because you mentioned that the membrane has the concentration limitation.
Yes.
So yeah, so how to choose which one is better fit for the fit solution?
Yeah, so this boils back down onto what the water is, what the concentration we are looking at. So if we are going to dive back into the theoretics of membrane and especially RO, so when we are looking at this, what is affecting my pressure selection or what is affecting my membrane selection? It's always on the osmotic pressure.
Yeah, so correct.
That's when we look into the concentrate side. So if we're looking into something along the range whereby 4 bars can work, there's a lot of brackish water membranes that's out there, up to 40 bars brackish water, up to 60, 70 bars seawater membranes are out there for us to use. Even if you are going to look into something that's ultra high, there's also ultra high pressure membranes that's available. So if we are going to talk into a lot more niche type membranes, we're going to look into 120 bar high COD, high solid content membranes, then DTRO is the way to go. So yes, the selection of membranes is a difficult choice. That's why there's a lot of process designers out there that specialize in this that will provide their opinion on how membrane selection can work. And basically that's the gist of Santa's works as well. So we provide the membranes. We also provide a clear-cut solution for you guys and tell you guys that, okay, for this type of solution, for this TDS, if you want to concentrate to 80 times or 80% recovery, what type of membrane should you use? And then we'll provide all these kind of opinions as well.
Okay, thank you very much. We have also one more question from the audience to Mr. Karen. So could you please comment that is it possible we can use the end-of-life RO membrane in your ZLD system? And yeah, you know, it's kind of the sustainable strategy to use the RO membrane modules. So could you please comment on this idea?
So us spending end-of-life membranes or for ZLD is actually not a very good idea. So what happens on ZLD systems? Basically, if you're going to design ZLD systems, the systems are going to be big. That's the first thing, right? The systems are going to be big. We're looking for maximized recoveries. The water standards, the recovered water need to be processors, so the standards need to be high as well. So if we're going to use end of life, what is going to be affected? First, the flux. You're going to need way more membranes for that. If you're going to, then we are going to look into the rejection rates. So at end of life, the rejection might get slightly less and less. So probably it's not as guaranteed at the start, whereby there's 99% rejection or even 95% rejection. It might drop down all the way to 90% rejection, whereby the TDS might not meet what the requirements for process reuse is. So typically we won't put up end-of-life membranes for these kind of users as well. We can consider in this way. If I'm going to create a zero liquid discharge system, I'm going to look at a long lifespan, right? For industries, probably 5 years, probably 10 years. If I'm going to put on a end-of-life membrane or a spent membrane, how long is it going to last? Is it going to only last me 2 months and I need to change it? Then the economical effect is no longer there.
Okay, thank you very much. And let me see. We have one more question, the last one for Mr. Karen. And the question is about the feasibility of the ZLD system in treating the pharmaceutical wastewater. And you know, this kind of water will have the feature of the high solvent, high COD, high TDS. And this water also can contain a lot of the toxic materials. So is it possible to use the ZLD system to treat this kind of the wastewater?
Yeah, so then again, it boils back down to how the overall process design is going to look like. So if you're going to look into pharmaceutical waste where there's high COD, solvent counts, what we are going to look at is actually, do we want to recover the solvents? If recovery the solvents like DMF, DMAC, acetone, acetic acid is something that is something to look at for us, then do we really want to just dump them all away using ZLD? Or do we want to recover and then get back as much of the solvents as possible first, maybe using distillation methods, triple effect, quadruple effect distillation, where we can get back a lot of the DMF, DMAC, and then when we look into the water discharge, the high CODs, the high toxicity, then we look into a combination of different membrane reactions. Maybe for the high COD, you can look into NBRs, AO, A2O. And then if you're going to look into something that's harder to break down, when there's benzenes, there's phenols, there's aromatics in there, do we want to use things like AOP for us to break it down before the AO? And then we can look into the simpler to do stuff, like the TDS, how do we actually concentrate it and then push it out towards a full complete zero liquid discharge. So it's not really about whether one single membrane system can solve the ZLD problem for all the world, but it's how actually the process design look into the water source and create a very curated, very specialized process flow for that specific water source, whereby we can hit the zero liquid discharge requirements and then make sure that the water is fit for reuse, while saving costs on resource recovery and all things like that. So
okay.
Yeah.
Okay. Thank you very much. It's really the nice answer about the questions. So we still have some questions for Professor Zhuo Jian and Professor Yang Xin. And the one is about the MD system, one is about how to overcome the challenge of the membrane whitening and the long-term stability in the real application of the MD system. We have to fabricate the hydrophobic membrane. So the problem is about the membrane whitening during the long-term process. So could you please have some comments on these questions?
Okay, sure. So actually for this membrane wetting, it is considered one of the major issue for the membrane distillation. Just like I mentioned, the other one is the energy consumption. So the second one is actually the membrane wetting. So for the membrane wetting, generally, I think what we can do is firstly for the design of the membranes. So when we are doing the design of the membranes, we can design the membrane with a special structure. So we can design the membrane with some of the surface modification. So to increase the hydrophobicity, even increase to superhydrophobic membranes. So those are the ways in the designing of the membranes. Then we also can overcome this issue by doing something on the process-wise, on the process scale. So in the process scale, there is an opportunity to remove the salts continuously so that we can reduce the wetting issue. And also we can do some of design some of the cleaning strategy. For example, for our pilot scale study, so we designed a simple cleaning strategy. Over the about 2-month operation, we didn't see any wetting issue. The conductivity of the permeate site maintains a very low values. So we do have a few ways that we can make use of to do the anti-wetting of the actual long-term operation. Yeah.
Thank you. So the one strategy is the membrane fabrication, and the way is to do the modification of the membrane. And then another strategy is the membrane cleaning, right?
Yes.
Okay, thank you. So Professor Yang Xin, do you have any comments for this question? How to overcome the membrane whitening problem?
Yeah, I think I agree with Professor Zhuo about all the comments about the membrane functionality and the process parameters. One of the things we also did all this in terms of creating a continuous membrane crystallization to actually avoid that supersaturation occurring near the membrane surface, right? And because when you actually have the nucleus is starting to develop near the surface, and that's where that wetting is seeing the opportunity to actually occur. So what we also did is more fundamentally, we dig into how the nucleation work is actually affecting. It's more on the surface, it's more on the bulk solution, and we develop a model that is actually will be able to help us see whether there is an operational window from changing or controlling the hydrodynamic point of view, that under that operational window that we can actually safely operate the system, avoiding the crystallization occurring on the surface, while we can safely allocate this crystallization in a crystallization vessel, as Professor Zhuo was sharing, right? So that kind of nice operation domains that we can also have some theoretical guidance. That's also our contribution to that. Yeah.
Okay, thank you very much. It's true. So I have just a follow-up question to Professor Yang Xin. So the one is we talk about a lot of strategy about experimental strategy on the membrane fabrication or modification. So is there any modeling strategy from the modeling side to see any solutions about the membrane whitening? You are the specialist about the MD modeling. So do you have some comments to share with us?
You mean to actually use the modeling to predict when wetting is going to occur? Okay. Yeah, it's a very complex problem. So what we are trying to do is we're trying to build like a MD, like it's a fouling model, right? So it's actually can see how when the fouling is going to occur on the surface and how that is actually can be linked to the surface energy of the membrane. When of course based on that correlation, that we can actually see when the surface energy is going to actually lower or higher, that is actually corresponding to the wetting moments. So in a way that we need to also use the experimental verifications, experimental results to verify whether this is consistent with our observation in terms of the flux, in terms of, the quality of the permeates. So that's something that we are actually trying to build at the moment. So it's a more comprehensive model that looks into the correlation of fouling and wetting and surface energy, and also the membrane performance itself. So yeah, it's a very interesting aspect to look at. Definitely very very useful for the practical applications.
Okay, thank you.
Yeah.
We have one question to Professor Zhuo Jian, and the audience is very curious about the economy feasibility of using the MD system to recover salt or the cleaning water from seawater brine. So could you please give some comments to evaluate the economy feasibility to compare it with RO system?
Okay, so actually, to compare with the RO system, before we go into the economical feasibility, I think the major one should be the technical feasibility. So for the RO system, if you want to recover additional water and additional salts from the brine, then the operational issue should be quite an issue for the RO because of the high pressure, high osmotic pressure. So probably the RO system may be very difficult, challenging to do the further concentration. But on the other hand, for the MD system, I think technically this is not going to be a challenge because it is not limited by the osmotic pressure. So the concentration of the salts will not be the limiting factor. So this is the first thing. Then the second thing regarding to the economic issues. So I think for using the MD to recover more water and more salts from the RO brine, one is to help to solve the environmental issue. So if we talk about the economic feasibility, that one should also be taken into consideration. Then the second is when we are doing the recovery, the value of the water and the salts recovered will be having some commercial values. In addition, this is not the only thing that this MD can do because MD can be coupled with other process. For example, if we want to recover the sodium, not sodium chloride, but just the sodiums, so sodium can become caustic soda, can be sodium carbonate. So we can use the MD process to do the first step of concentration to concentrate the solution to more than 10 weight%, so that we can have a follow-up step. For example, the coral alkaline process to produce the caustic soda, or even to produce the food-grade sodium carbonate. So that will be additional advantage. Yeah.
Okay. Thank you very much. Thank you for the very good explanation about these questions. So this is all about the Q&A sessions. Thank you very much for your attending, for the very nice explanation about the questions and explanation about your research and background. So before the end of the webinar, let's welcome Joanne to introduce SGMAN program for the SIWW 2022. Hi, Joanne.
Well, I'm bringing up the slide. I just want to really extend a warm and very heartfelt thanks to all the speakers. It was excellent. We really had a perspective from academia all the way to industry, and also the audience. I mean, very practical, very tough questions, and I think it's answered really well. I think it also helped to dispel some of the myths surrounding MD. Some people think, it can never be done, but obviously there is, and it may not just be the membranes, but process-wise. So really happy about that. I know we're running a little bit late. I'm just going to steal just 30 seconds of your time. As SGMem, again, 2 years after COVID, haven't met anybody face to face. We are actually going to be in person. We took a booth under the Singapore Pavilion in SIWW 2022. So this is happening 17th to 21st of April at the STANS Expo in MBS. Please come and visit us. This is our booth. But very interestingly, what we also have 2 programs that we put together. One on April 19th, the other on the 20th. Again, the theme around all of this is based on sustainability and the need for using technology for creating a greater good, actually. So for the product showcase, we are happy to have NTU and NUS there showcasing their membranes beyond the lab. Actually, both of them I think have already reached a pilot or higher stage. And then we have fireside chats with 2 of our industry members, Basir from Liquinex and Miao from Arkema. So again, they'll be talking about very, hopefully thought-provoking topics, end-of-life membranes, green membranes, biopolymers. So again, do join us in person. I believe if you come in as a trade visitor, it's free, but you do need to register online. Please come and visit us, and look forward to seeing you there. So again, thank you very much, and have a great day.
Thank you. Bye-bye.
Bye-bye. Thank you.
Thank you.
Thank you.
Thank you.